So let's try and measure some active devices and see the dynamic behavior of some amplifier. This is a variable gain amplifier whose gain can be adjusted with an analog control pin, and it of course has a power supply connected to it. The power supply is coming all the way from up here from the really nice Roden Shores NGP800 power supply. So what I really wanted to do was essentially control the gain of this amplifier with some waveform and then trigger the network analyzer to follow that waveform so we could make a synchronized measurement. So here's the S parameter measurement of the amplifier when the amplifier has no power. And we can note right away that the input return loss is very good, even though the amplifier has no power, meaning the input must be much more passively matched than actively matched. Now the output, the S22 is at -3.5, and we expect it to be much better than that for this amplifier, and that's because the output of the amplifier is most likely much more actively matched, and therefore it needs some current in the final stage. The S12 and S21 are very low. This amplifier does have very good isolation when it's not powered, which is to be expected. So we can go ahead and apply power and see what happens. Here we go. Now as soon as I apply power, we can see we don't really see much of a difference in S11, but the S22 does get significantly better as expected because this is an actively matched amplifier at the output. The S12 is very low, meaning it does have very good reverse isolation. Now on the other side, in the S21, we are now up to 28.6 dB of gain at 500 megahertz, which is what we expect. Right now the gain control of the circuit is held at 0 volts, which is the maximum gain of this amplifier, which all looks really great. Now what I can do is I can change the way that gain control is done. I can apply a square wave to it. And if I apply a square wave, I would expect this to jump up and down depending on whether on the high side or the low side of the square waveform. Let's just go ahead and apply that. So here's our square waveform. And we can indeed see that this is a 1 Hertz square wave, and the gain jumps from about -5 to +28. So there's a 33, 34 dB of gain control, which is great. And this means that we're going to be able to use this in an AGC loop, for example, to do automatic gain control. And the output return loss does change a little bit between the two states, but not by much. Most of these parameters are reasonably constant. Now I can go ahead and increase the frequency of this square wave. And normally what I would want to do is to trigger the VNA with this square wave so we can actually get a synchronized measurement, but it's not possible here because a bug in the firmware, but we can change the frequency nonetheless. There you go. Let's go all the way to 50 Hertz or so. And at 50 Hertz, we should see some cool effects. Here we go. So we see this kind of rolling effect. That's because we're aliasing the update rate of the VNA combined with the actual waveform I'm applying. Now right now we're sitting at a -20 dBm input power, which is pretty important because we want to make sure that we do not saturate this amplifier. So -20 dBm with about 30 dB of gain is +10 dBm. It's getting close to the saturation of this amplifier. But unfortunately I cannot go below -20. You would need an external attenuator on top of that. Everything else doesn't seem to change much. We're at 601 points and the IF bandwidth is 70 kilohertz, so about 50 hertz seems to be our update rate. Now in this condition is nice and we can see this effect, but really what we want to see is in a zero span. We want to see the S parameter as a function of time rather than a function of frequency, and then we can see how fast we can trigger the instrument, at least internally, to see how fast of a change in gain control we can observe. So here's the new configuration. I've changed a few things. First of all, we're looking at a single frequency of 500 megahertz. We're looking at S11 and S22 on the Smith chart. At the top right, we have S21, as we were looking at before, except that I have changed the gain control not to be a square wave, but rather a sinusoid. And therefore, we can see the kind of sinusoid behavior of the gain, not being perfectly sinusoidal, but it does follow that shape. Now at the bottom left, instead of plotting S12, which is kind of pointless, I'm plotting the phase of S21. So this tells us how the phase of the amplifier changes as a function of its gain. Now normally, ideally, you would want the amplifier to not have any phase changes as you control its gain. But clearly in this amplifier, we have quite a bit of phase variation as we control the gain, and you can see the correlation of the phase to the gain. Right now, the gain control is happening at 50 Hertz, just like before. We're looking at 751 points, spanning essentially the entire time that it takes to see multiple waveforms at 50 Hertz. So I can increase the frequency that we're applying here. So for example, I can go to 200 Hertz, and at 200 Hertz we can still see that we have multiple cycles. So this is exactly what you would expect. It's just too bad that we can't trigger this, otherwise it would be much nicer. Now I can go over here and change the number of points. So if I go on the sweep type over here and actually change the number of points, we can make the number of points much less, which obviously will have a much faster sweep. So let's put it at 100 points and keep increasing the frequency and see how fast we can go and still see a change. So I'm going to put it at 4 kilohertz. So we are now changing the gain at 4 kilohertz, which is quite fast. And I can kind of still see it a little bit. That's probably at the edge. So it means that if you have about 30 points or so, you can still see a fairly fast change in the gain control. Let me go down a little bit. let's say 3.5 kilohertz or so, you can still see the top and the bottom values, just not triggered. And you can see that S11 and S22 don't change much across these gain control value, which we saw also on the magnitude of S11 and S22. But using this technique, if you were to combine it with the triggering, you can actually get a lot of information about the behavior of various amplifiers as a dynamic function of time, which is one of the nice things about having a network analyzer.